Yeah. Good morning, everyone. So today Dr. Prashant Kumar is among us. He's one of the senior scientists working in Space Application Center, ISRO Ahmedabad. Now, he's been working in SAC Ahmedabad for the last 16 years, and his major research area is on particle filter data assimilation. This is something very different from whatever you have studied till now, variational methods, ensemble, Kalman filter, all different types of Kalman filter, where we assumed everything is Gaussian. Now this particle filter allows you to handle or take care of non-Gaussian effects also. And so I'm sure that all of you will enjoy. Now I have myself heard him some 3-4 years back, and I'm very keen to listen to him. So let us invite Dr. Prashant Kumar for his talk today on application of particle filter data assimilation. Thank you.
Thank you, sir. Good morning, everyone. So my presentation is mostly on the assimilation of satellite data, because as you can understand, I am from the Space Application Center, Ahmedabad. So where our more focus on the applications of the satellite. So with this background, I will start. And then I assume that you have a very good background on the mathematical formulations of the data assimilation, because last week is totally dedicated on this. And with that, you also have some idea about the operational implementation of data assimilation, because in this week, mostly lectures are on the real world applications. Okay, so within that, there is one theory which is based on non-Gaussian, non-linear conditions. So I will touch that, and within that, I will tell you first that why this problem arises. Okay, so if we will start that, who uses the satellite data? So if we will, because as a atmospheric scientist, I can say that I will mostly talk about the atmospheric model. So around 95% observations which are assimilated in the weather model or atmospheric model are coming from the satellite. Rest 5% are coming from the other conventional instruments like radio sondi, synop, etc. Okay. Now, here you can see that how the observations which are available from satellite and other sources are increases. It increases around 5-folds in the last 15 years from 2000 to 2015. And this data is continuously increasing. Now, out of that, the total data which we received from various sources, suppose if we will consider that as 100%, which is around 239-40 million in 2015 framework, we will find out that only few percentage are useful for data assimilation. Means out of 100%, only 7% data is useful or selected for the data assimilation application in the real world problems. And within that 7%, only few percents are finally assimilated in the weather model. And even that, this few percents are just 95% contribution from the satellite. So now you can understand that most of the data we are not able to use in the applications. Okay, so just a rough framework I will tell. Like we have one InSat satellite series. Within that we have one imager. Okay, it's a multispectral imager. Multispectral means we have a very few channels, like 6 channels we have. Within these 6 channels, one is in the visible, whose resolution is roughly 1 kilometer. Visible, its resolution is 1 kilometer. Then similarly we have a next channel Short wave infrared, this is also 1 kilometer resolution. Then we have a MIR, TIR1. So these channels are based on their frequency. TIR2, these 3 channels are at 4 kilometer and 1 channel is available at 8 kilometer resolution. So data assimilation community tell that we are not able to assimilate these visible channel, which is 1 kilometer over a very large region. It's cover around 10 degree east to 150 degree east, minus 50 degree to plus 50 degree in latitudes. Okay, so we are not able to use this visible channel. So here also they face same problem. Then they told that in MIR, TIR1, TIR2, they have an issue with the surface emissivity. Because of that, they are not able to assimilate. So only data which is finally used in the assimilation system is just a 8 kilometer of my water vapor channel. It's a very big coverage. If you will go on the IMD website or our website MOSDEC, you will get that it will cover a very large region. But only this particular channel we are able to use. Similar to our multispectral channel, goes in US, they have a advanced imager. They have around 16 channels in place of our 6 channel. In that also the condition is same. They are only able to use water vapor channel. Okay, so same problem arises with the CBRI also. Okay, and others space agency. Now within that, when we will go for water vapor channel, then again they told that no, we cannot assimilate cloudy conditions. We will assimilate only clear sky radiance, because definitely some radiance assimilation part will be covered by someone. Okay, so they told that okay, I will not assimilate clear all sky conditions. I will only assimilate clear sky. Okay, when no cloud is there for IR condition. IR means infrared channel. Okay, so if we will assume in general around 60 to 70% of the atmosphere is covered by cloud. So again, we rejected the data set. Now we reduce this data set again further, because now we are using only 30 to 40% of the data due to the conditions of using only clear sky radiances. Okay. Then further, because here we have a every 8 kilometer pixel. Then they will told that no, we cannot, even now also we cannot assimilate this 8 kilometer data completely due to some correlation in the observations, okay, with nearby points. Then they told that I will use some smart things, thinning, super robbing, and then finally they assimilate the data at 120 kilometer. Okay, so this is the scenario in which most of the operational agencies are using the satellite data. Okay, this is just one example. Similar to that, we have another example, like there are some hyperspectral sounders. So like in India, we have a multispectral sounder, which contains around 18 channels, but it is in the geostationary platform. I believe you know what is geostationary and polar orbiting orbiting orbits. Okay, so in geostationary orbit means this INSAT 3D sounder will give the measurement every half hour or 1 hour. Okay, but in polar orbiting there are some hyperspectral satellites which have around 8,000 of the channels in place of 18 channels which we have in the geostationary platform. They have around 8,000 channels, 8,400 channels something in polar orbiting. Okay, but again they will tell that okay, we cannot use these all channels, we will use some combination, okay, maybe some partially independent, and then finally out of 8,400 channels they are assimilating only 300 channels right now. Okay, so this is the issue which we can consider that it's a Okay, so this is the well-known theory. You know, because last week, because you go with the basic mathematical formulation. So here we can consider this as a, in numerical analysis, we also consider this as a prediction correction formula, or in Kalman theory also they use update. Okay, so every time we don't know what is my true state of the atmosphere, but we have some observation in between. Okay, and this model simulation says something like this, and then we use some correction or update and try to find out my analysis, which is a combination of my background and observations. Okay, and like this we move. Okay, because now you have a good understanding of these things. Okay, and long back, the idea is that we have some sparse observations and we want to fit a regular, physically consistent best state of the atmosphere. But now the scenario is that we have sufficient number of measurements also. And now we need to think that how we can use this observation also potentially, because now the dimension of observation is also very high. It's not like earlier we told that it is 10 to the power 6 or something. Now the dimension is of observation space is also very high. But parallelly, the dimension of model space is also increasing. Now people are working on higher and higher resolution. Okay, previously they work on 9 kilometer, 10 kilometer. Now they are running the model at 1 kilometer, even in meter resolution also. Like in NCMRWF, they are running one model at 300 meter resolution. Okay, 330 something. Okay, so now as you increase you will face the problem of cost of computation as you change the methodology from variational and Kalman filter. Then there are different variants of Kalman filter. Okay, and then in theory there is a one method which is a particle filter. Okay, and maybe in future there will be much more. Okay, so this is a problem where we are dealing with the non-linearity and non-Gaussianity. Okay, because everywhere we face some assumptions, like in variational also we use some assumptions, constraint, linear, unbiased, Gaussian. Then in Kalman also we use some assumptions, and then because we are now running model at very high resolution, observation, we want to exploit all the observations, then definitely we need a methodology which can handle this problem. Okay, so this is just a motivation, and then this thing also, you know, there are so many sources of error in my initial condition, error in my model, as well as error in my observations. Okay, and with this we also have a limitations. Okay, so those things you already covered in your last weeks. Okay, so now I have two more points which we need to discuss, how we check the impact of the observations. Okay, so maybe is there someone who discussed this thing? OSC, observing system simulation experiment, observing sensitivity experiment, or adjoint sensitivity experiment? No? Okay, so how we...
Yesterday Arya discussed this, OSC and OSSC.
And you know about this thing. Okay, so there are two well-known techniques. One is based on the observing system simulation or observation sensitivity experiment based experiment. Another is the forecast sensitivity to observation, or also known as adjoint sensitivity. So within that, we assimilate our new sensors or satellite, and we try to find out that which sensor have a impact, or which kind of sensors are required. Sensor means what kind of satellite we required in the future. Okay, so now suppose if we have a one data set in which the value of my R is very less, then what will happen? This kind of experiment, data denial experiment or data addition experiment, will give you that this new data have a negative impact. But adjoint sensitivity will tell that this particular data set have a maximum error, maximum impact. But on the other side, if we will use identical satellites, like maybe two INSAT series, INSAT 3D satellite and INSAT 3DR, okay? And then what will happen? This kind of experiment will show that first one, the data which assimilated first have a large impact, and second satellite which contains the identical information have a less impact. But on the other side, adjoint sensitivity will tell that it will both have a same impact. Okay, so how we did the adjoint sensitivity? Someone can tell that? Actually in general, when we did the adjoint sensitivity, we generate one analysis with the help of Y and XF. We generate one XA, which is my X analysis. Then from analysis, we give one prediction, XF. Then at the time of XF, we defined a one cost function. Maybe you can call this as a F or maybe J, a cost function based on the some truth available at that time. And then we use the adjoint model, and from delta J upon delta XA, we calculate the value of delta J upon delta, delta J upon delta XF. At the time of forecast, we calculate the value of delta J by delta XA. Now, you know this thing, XA is equal to your XB plus K time Y minus H of XB. Now, from here you can find out that your delta XA by delta Y is equal to K. Now, you know the value of delta J by delta XA. You know the value of delta XA by delta Y. So, delta J by delta Y is equal to delta J upon delta XA into delta XA upon delta Y. Now, this thing is simply your Kalman gain, and this thing you know from your tangent linear model. So, based on that, now you able to get that corresponding to your cost function, what is the impact of different observations. So, this methodology is widely used to assess the impact of different instruments. Not only the different instruments, it will also tell that what kind of measurements are required, whether you need more wind sensor or you want a temperature or moisture sensor. So now, observing system experiments are sensitive to the change of order. So if you assimilate similar kind of informations, then first one will give a impact, another will give a negative impact. Okay, so but both are correct, and we need to define at what time we need to use which methodology. Okay, and there are some advances, like Professor Kalne did some work, proactive FSO, and like this there are a lot of research that how we improve this methodology. Okay, now this is again one scenario in which we define the resolution versus the data assimilation technique. Okay, what's tell that if you are working on a very coarse resolution, these assumptions are valid. Means we can use this kind of techniques. But as you are increasing your model resolution, your system is no more linear Gaussian. So you need to move towards the Gaussian nonlinear DA and further a fully Bayesian nonlinear DA. Okay. Okay, so with time also, but I consider this as a initial value problem. So mostly I am focused up to the week time. Okay, so now these details you also read. You read about the conditional probability. You assume that my distributions are Gaussian for background as well as for the observation. Okay, and we assume that these distributions are mutually exclusive. Okay, and Gaussian also, because of that the joint probability distribution can be taken from the base. Okay, so because everything you have some idea, okay, based on your prior inputs. Okay, so now this original problem is a multiplication problem. Okay, nowhere base assumptions is that it's a optimization problem or it's a linear problem. It's simply told that it's a multiplication problem. Okay, within that we need to multiply prior with the likelihood. Okay, but what we did, we assume that both the distribution, both the world are Gaussian, both are mutually exclusive. Then we find a fantastic cost function. We try to minimize it, use some well-known theorems, Gauss-Markov theorem, which told that the least square solution is the best solution. Definitely Baran sir discussed that. Least square solution is the best solution for all possible solution, or for linear operator, and then a kind of a extension in the nonlinear space, that Rao-Blackwell theorem, which told that not only for the nonlinear observation operator, least square solution is the best solution if my distributions are Gaussian. Okay, so all these problems comes because we consider that, we assume that my distributions are Gaussian, they are independent, and this thinning problem also arises from there because we assume that nearest the observations are independent. Okay, to make my observation independent, I want two observations which are far away, sufficiently far away. That's the reason we are not using the actual observation, we are using a kind of a mean value of a very bigger region. In place of assimilating data at final resolution, 8 km or something, in inside case, we are assimilating data in the 120 or 200. Normally in global model, they are using the 150 km as a thinning. Okay, so we are assimilating data at very coarse resolution. Okay, so now we have some few issues in all the models, like in optimum interpolation 3D bar, we are using some fixed background error. In 4D bar, explicit background error is fixed, but implicitly we are flowing the background error in some 4D bar codes. Okay, like in ECMWF, they are using the implicit flow of the background error. Okay, but in some model that facility is not available. Okay, but ideally my background error covariance should be system or condition dependent. Okay, then there is a one known theory based on the Kalman which told that we can assess the flow of the background error covariance, and it's become very popular because of there are some heavy extreme events in which we cannot use the fixed background error. My background error covariance should be based on that extreme events. Okay. Okay, sorry. So then within that ENKF is there. Okay, it is better than extended Kalman filter because we did not take any linearizations. Okay, so still there are some issues in the ensemble Kalman filter. Okay, one problem is that the ensemble Kalman filter depend on the size of ensembles. Okay, but for large scale or high dimensional problem, generating a very large number of ensemble is itself a issue. Okay. Now, because of the limited number of ensembles, there are some issues. Okay. So these well-known issues are inbreeding, a kind of a underestimating the ensemble variance, filter divergence, and spurious correlation. So for this, they develop some technique based on inflation and localization. Okay. And then they find out that, okay, so in this regard, people tried a lot. They did some work that how many ensembles are needed. So Professor Miyoshi in Recon, Japan, they have a very big computer. Once upon a time, it's the biggest computer of the world. Okay, Recon computer. So he performed 10,000 something ensembles. And even that also, they are not able to find out the full PDF. Okay, so he published so many literature on that. How many ensembles are sufficient? Okay, but still it is a problem. Then
Sir,
localization. Localization is generally used to avoid the spurious correlation. Definitely Arya discussed this thing yesterday. Okay. And then inflation. Inflation also he discussed yesterday. Okay. To avoid the filter divergence. Okay. Now, there are methodology which is based on the hybrid methods, which is a combination of best of two worlds. The flow of background error covariance concept can be taken from the Kalman theory, and utilization of nonlinear observation operator theory can be taken from the variational method. And that's the reason in almost most of the center, except few, hybrid methods become very popular. Hybrid methods means in which data are assimilated using the variational method, either 3D bar or 4D bar. Like 4D bar is used in the NCMRWF, UK Met Office, ECMWF. 3D bar is still using in the NCEP. Okay, and then flow of background error covariance part is taken by Kalman filters, different variants of Kalman filter. Like few centers are using ensemble transform Kalman filter, but there are few centers like Japan Meteorological Agency. They are purely based on the ensemble theory, like LETKF they are using for flow of background error as well as for assimilating data. Like this, Korean Institute also using the fully Kalman filter based theory. Okay, so now there is possibly one point that we can think that beyond the Kalman filtering. Okay, so in ENKF we assume that my all things are Gaussian. Okay, so the point is that is this assumption is valid for a dynamical model? Because the optimality of the Kalman filter is no longer preserved. Okay. Now I have a one example for this. Okay. Okay. So and then the another point is that what if my distribution is not Gaussian? Okay. So in literature, fully non-Gaussian data assimilation method exists, but none has been proven for large scale problem. Still, researchers are trying on that. They did some work, mainly Professor Levon from Europe, and then Professor Ducott. There are few groups who are working on particle filter theory. Okay, and then particle filter is also, people try to use particle filter in this problem also. Okay, but within that we have a one issue which is very popularly known as a curse of dimensionality. Okay, so the point is that how we introduce the or how we neglect the condition of Gaussianity in the data assimilation. Okay, so how non-Gaussian condition arise in the weather model. So suppose In this, we have a model state xn plus 1, which can be write in the form of a nonlinear model M xn plus a random error term. Okay, and I assume that my xn and Rn plus both are Gaussian. But now I assume that my model is nonlinear, it's a quadratic. And what we find out that even my xn and Rn both have a Gaussian distribution. The distribution of my xn plus 1 is not Gaussian. Okay, so how we perform the assimilation, or how we perform in the weather forecast in general, we use some kind of a cyclic assimilation. Every time we assimilate the data, we give a forecast like next 10 days or 5 days. Then we give a short forecast, 6 hour or 12 hour. Then again we assimilate and give a forecast for next 10 days. Okay, so it's a well-known theory. Maybe someone discussed this thing. Okay, so but this problem told that even if you have a quadratic term here, your next prediction is not at all a Gaussian. So when we assume that the distribution of my background is Gaussian, this is not very clear, because our weather models or other models are based on some non-linear equations, mainly the different laws of conservation laws, okay, conservation of, and those equations are mostly non-linear partial differential equation, okay. So definitely their solution will not be in the form of linear, and we assume that my this xn plus 1 forecast time we have a, okay. The next thing is that this same condition hold with the my yn also. If my xn and sn both are Gaussian, and suppose my h is also nonlinear, my operator is nonlinear, observation operator, then also my yn is not hold this condition, okay. So in general, when we assimilate the radiances, what we will do, we use some radiated transfer model. Radiated transfer model means it's a kind of a, it's a integral differential equation, okay. So that differential equation is solved, and definitely its solution is not it's a highly nonlinear equation, okay. We take some approximation, but it's not at all a nonlinear. It's not at all it's a linear, okay. But so again, the same problem arises. We are not in the Gaussian space any time. So within some framework around, I think at the same time, there are some theory came in which people start working on that conversion of non-Gaussian data set into the Gaussian, a kind of a Gaussian transformation. Okay, they did some work like, if I want to assimilate the rainfall, and the distribution of rainfall is not Gaussian, it's a kind of some binomial distribution, log normal. Okay, so what they did, they convert their distribution from log normal to the Gaussian, and then they assimilate this. And some theory also came at the same time that in place of assimilating everything in a Gaussian framework, they use some different framework, okay. So like this, some research also performed. Okay, so now again, we have a problem from the Bayes theorem. Okay, so we have a parity distribution, and we also have a likelihood. Okay, so now I have few slides for basic framework of the particle filter. Okay, so in this theory, I use sufficiently large ensembles from the model space. Okay, and then we gave the weights to my ensembles. Okay, Now these weights are given based on the likelihood. So because we have a observation at a time step. Okay. So my weights are mostly based on my likelihood distribution. Okay. So now in this framework, nowhere we assume that any linear assumption, any requirement of a big problem like generating a tangent linear model of a full nonlinear model is a very big work, because if you want to write a linear physics for a nonlinear cloud physics itself is a very big problem. Okay, and whenever someone is using 4D bar, they are using some kind of a linear physics assumption. Okay, and you can understand that cloud physics, microphysics, how good is their linear assumption. Okay, so for that they use some tangent linear versus adjoint test, this TL versus NL test. After how many hours my tangent linear prediction will be totally fail. Okay, so lot of theory came because of this tangent linear and adjoint conditions. Okay, another benefit is that we are not changing the first case in this condition. What will happen whenever we assimilate some observations? We are changing my x. Okay, so what will happen, and that change in my x is depend upon my error covariance. Okay, how it will happen? Suppose I want to assimilate the temperature or moisture. I will generate a background error covariance corresponding to this 2 degree centigrade change in my temperature. How much changes will be possible in my wind, in my pressure, etc. Okay, so this part is done by background error covariance. Okay, and not only, suppose if I will assimilate temperature information at the surface, it will not change only on the surface, it will change on the all other vertical levels. Okay, so because we need my condition, my state in the balance. Okay, but now you know that, because now we are almost at the end of this workshop. Now you know that whatever background error we are generating, that is not complete. So in some way you are disturbing the balance of your first case. Clear? Okay, so now here the weights is the normalized value of the PDF, and suppose if we will take the Gaussian distribution, in that condition my weight will be look like this. Okay, and definitely Varahan sir told a lot about this type of cost function. Okay, okay, so now we already discussed that we don't need the covariances here. Okay, so now this is a very complicated issue in the variational theory, because we need covariance estimations. In sequential method, this Kalman filter also we need a covariance estimation. Okay, then the performance of this ENKF or other methods, they are enhanced with the help of some methods like inflation, localization. Now people are working on that, some kind of a adaptive inflation or localization. Okay, because earlier most of the work are performed that they took the fixed value of localization. Now based on the conditions, they find out that how we change the values of localization in different region, or a kind of a adaptive values. Okay. Okay, so definitely this issue we don't have. Now, what is the problem with this? Suppose we start with the sufficiently large ensemble members. Okay, then what will happen? We will, in this methodology, we will select only those ensembles, or in this theory we call this as a particles, which are closer to my likelihood. Okay, then what will happen? Most of these ensembles or particles will be rejected and we will select only few members. Okay, then after next time what will happen? This number will be again reduced, and after some time what will happen? You will get only one particle which will take all the weights, and that is the issue in this filter. Okay. So what is this degeneracy? With each new set of observation, the old weights are multiplied by the new weights. Okay, so what will happen? Very soon, only one particle has all the weights and rest all the particle will be discarded. Okay, and this is the issue which divert us from our basic assumptions of the distribution, which told that we start with a large number of set and finally we have only one single prediction. So there are some solutions which are based on some sequential importance resampling or some kind of proposal density. Okay, so people tried this and they try to find out that in which condition for high dimensional problem we can use this method. Okay, so what they find out that even with the sequential importance resampling, they found that this issue of degeneracy is not resolved. Okay, then even in this condition also they found that after a certain time period, the other weights are very small. Okay, so to resolve this issue, there are some work which is based on the, again, based on the theory of the ensemble Kahneman filter, where they consider the localization. So they develop some methodology like local particle filter, in which again they consider the concept of the localization, inflation, etc. Okay, then parallelly, Luhmann also developed one filter, equal weight particle filter, and he mentioned that this filter can be used for a high dimensional problem. In one of his work, he showed that this kind of filter will be work. Okay, then this is not very known, that people think that suppose if after some 10 time period my filter is not correct, then we will restart my filter after a certain time period. Okay. So now this is one concept in which he told that we will select the particle from the proposal density or importance density, and only those particles we will use which follow in my proposal density. Okay, and this formulation is he proved for the high dimensional system also, and not only that, he generate the model error also using this proposal density concept for equal weight particle filter. Okay, so based on that, okay, we also tried some work for assimilating our Indian satellite INSAT 3D. So within that we have a one TIR1 channel. Okay, so initially I told that this TIR1 channel is not used for the assimilation in general. Okay, then but we can simulate, or we have a observation operator for that. Means our radiated transfer model can simulate the radiances or brightness temperature from the model fields, but still we are not using this for the assimilation. Okay, so the idea is that can we use this one additional data set in the model setup so that One benefit is that we are adding some additional information which earlier is not used. Another thing is, can we use particle filter theory for that? Okay. So what we did okay. So in this concept, one thing is that using the all sky conditions TIR observation is itself is a big concern, because there are few papers only in which people are assimilating all sky radiances, okay, but still clear sky radiance is popular. In most of the centers, only people assimilating the clear sky radiances. So one thing is, we tried here that we use the TIR1 channel, which in general not assimilated in the weather model. Okay. Another point is, we also try to assimilate the all sky conditions. Okay. Then for this, we use some kind of a hybrid concept, because I already have a one framework in which we assimilated the other measurements, conventional other satellite measurements, using the variational method or ensemble Kalman. So one of the framework is that in which we are using the 3D bar. Here I use the 3D bar for assimilating all kind of conventional satellite observation, so that whatever improvement will be in this experiment, that will be over the whatever we have presently state of art. Okay. Then in addition to this, I use a similar experiment in which, in addition to 3D bar, whatever data is used or assimilated in this experiment, over through that we also use all sky TIR channel. Okay, so this is my design of experiments. I perform two identical experiments, one with variational method only, in which I use all the conventional and satellite observation. Another experiment is in which, in addition to my control, I also included the satellite radiances, which are in general not used for the assimilation. Okay. Okay, so now in this, what I did, we make various ensembles, or we can say particle, using diverse model physics. Okay, because I use WARF model. If someone of you use that, there are huge number of microphysics, cumulus physics, and many more things. Okay. Okay, so now in this, to assign the weight to my different ensembles of particles, I use two concepts. One is, whatever brightness temperature I simulated from the radiated transfer model, I compare with the satellite values at that time. Okay. Then with that, because we assimilated the all sky condition, so cloud, whether model is able to predict the cloud correctly or not, that is also one major conditions. Okay, so I put two conditions mainly here. One is on the what is my quality of simulated brightness temperature using the measured brightness temperature. Another is how good is my cloud in the prediction. Okay, now what will happen after this? There are few particles which will be rejected based on the performance. Okay, so what I did here, 50% particles I selected based on the performance. Okay, using some kind of a median filter, and then from the selected particle I again generate new particle. Okay, so that my total number of particles or ensemble will be same. So okay, I have figure for that. Okay, so now I give one more kind of a perturbation. So in general, to generate the ensembles, people use different methods. Okay, so one method will be the based on different model physics. Another method is based on the This theory, stochastic kinetic energy backscatter scheme. One more theory is that SPP, this we know popularly known as SCAPS. Then one more theory is that stochastic parameter perturbation tendency, SPPT. Okay, so like this, there are some theories on which we use different ensemble members. So to generate my new particle, after rejecting few particles in my previous time step based on the performance of my brightness, temperature and cloud. Now I
Excuse me, sir. Exactly how many ensemble members you are using?
in my next slide it is there.
Okay.
So now I reproduce new members from the selected particles so that my total number of members will be same. Okay. So now this is the figure. So I start with 2 different planetary boundary layer physics, 4 different microphysics, and I think 14 or 16 cumulus physics. Initially, I start with the almost same number, 23, 23, 23 for all the microphysics, 8, 8, and because of some mismatch in the combination, some physics are not working with some different physics. Okay. So initially, all the particles or all the members have a equal weight. Then I gave the 6-hour forecast, select the particle, new particles. Then from the selected particle, I again give a further perturbation based on SCAP method, stochastic kinetic energy method, and again I generated same number of particles here. So like this, we perform a cyclic assimilation for 4 time step every 6 hourly, and after that I give a prediction for a cyclonic condition. Okay, so this is my framework, how I perform this experiment. Okay, and then this is the condition based on different check on cloud and variances on the inset for clear and cloudy conditions. Okay, because this is one very popular problem in simulation of the all sky from the weather model. Because what will happen in weather model, it will show many places as a cloudy, which in actual there is no cloud, and vice versa is also possible. Okay, so this correction is also needed. Now, okay, so now this is same thing, whatever we discussed. So particle having higher weight are resampled at the observation time. So in this, we generate the new particles using this SCAP method so that my total number of particles will be same, 92 here. And in this methodology of SCAPs, we give the perturbation in the some fixed parameter in the parameterizations. Okay. So the idea is to that we want to focus on the high probability region or target PDF, so that with the condition of fixed number of particle, we will get the better estimation. Okay. So now I have few results for that. So this is my observed TIR1BT. So now here you can see that what is my RMS in joint RMS in all the ensemble based on all ensembles. Then this is the particle filter experiment, and this is a kind of a improvement parameter. Wherever it is positive, it show improvement, and negative means it shows some degradation. Okay, so I got some few regions I got some mixed results, and at few regions I got very good improvement, and this region is mainly which is influenced by the cyclone. Okay, but in track also what we find out that, okay, so one is the well-known issue that my starting point from the weather model when we start from the analysis and observed center location from the IMD or JTWC. I am not confirmed. It's IMD. Okay. There is a sufficiently large difference. Okay. And it's a well-known problem. Even the best track from the IMD, from JTWC, they also differ by 100 of kilometers. Okay. So even in this case also, I found that the center position in my analysis, which I take from the INCEP analysis, final analysis, and center detected by IMD, they have a sufficient difference. Okay. And then here you can see the track error. So almost at all the time step, we found a improvement with this framework. Okay, so now not only in the track forecast, what we found out that whether my basic fields are also changes, what happened with my basic parameter, temperature, moisture and humidity. So here we plot the improvement in humidity, temperature and wind speed. Again, positive value is improvement, negative is degradation. And what we found out that we got a good improvement over different levels. So what we found out that after utilizing this framework, not only my brightness temperature is improved, it also improved my basic fields, temperature, moisture, wind, etc. Okay. So now, okay, so based on this theory, I also tried one more experiment because in general, there are few data sets which are not used for the assimilation directly, like rain. Rain is also one measurement which is very rarely used for directly for the assimilation. Okay, so okay, but this parameter is very important. Okay, because and it's very complicated also. So it's always people think that how we can use such type of parameter which are very crucial. Okay, like rainfall. Rainfall is one of them. Then assimilating directly clouds. Okay, like assimilation of directly, if we can use cloud, maybe cloud mass directly or different hydrometers directly. Okay, so that kind of assimilation is really a very good problem. So okay, so this work is regarding that only, and then rainfall assimilation is definitely a very good choice if we can do it. Okay, so okay, before that I did some work, and okay, and before that there are a lot of work in I think in 1980 or 90s, 2000 time frame, when Dr. Krishnamurthy also did some work on rain assimilation, rain rate assimilation. And at that time, they mentioned that because of the large nonlinearity and non-Gaussianity, assimilation of this kind of parameter have a very short impact. Means after a certain time period, its impact is reduces. The reason is that at that time, they use a very strict quality control. Okay, so how we use this quality control in the weather model? So when we assimilate the data, we use some assumptions. My observation, the difference between observation and background should not be more than some 5 times or 3 times of my sigma O. Okay, so these kind of checks are used to avoid a very far observations. Okay, so then I did some work that how the quality control is important for in terms of the rainfall estimation. At the same time, Lin is also there. He did some work on the conversion of non-Gaussian to Gaussian for rainfall estimation. Okay, and then okay, and then at the same time, I also tried something that how the first guess is crucial for the rainfall estimation. Okay, because If my first guess is very far from the this rainfall thing, then what will happen? We will not able to assimilate. Okay. Okay. So now, but in this study, my objective was that how we can use directly the measured rainfall. Like there are sensors known as a gauge, rain gauges. They measure the rainfall. Can we use directly this type of observations in the assimilation? And in earlier experiment, I tried to assimilate the rainfall from the satellites directly, like from INSAT or from JAXA. They are providing the some merged type of rainfall product. Gauge, we normally call this as a gauge adjusted. Gauge adjusted means over the generation of a merged rainfall using infrared and microwave sensor, they corrected the rainfall over mostly over land using the rain gauges. Okay, so in general we consider this merged rainfall or gauge adjusted rainfall as a standard product. Okay, so okay, so now in because this rainfall is not a direct parameter, or maybe a we can say that it's a state parameter in the weather model. It's a kind of a deterministic, or we can say that it will generate after a certain time period. Okay, so when you will check your initial condition, the value of rainfall is not there. It will be initialized as a 0 whenever you will start your model. Okay, so how we use rain as a assimilation in 3D bar or 4D bar. We run the model for next few hours, maybe 3 or 4 hours. Then within that time frame, we will get some rainfall prediction from the weather model. And then we try to assimilate this in the, means corresponding to that 6 hour, we also have a we also have a measured rainfall, and then we can use this theory of 4D bar to assimilate this thing. Okay, so most of the work are earlier on that how to change the distribution from non-Gaussian to not Gaussian, or what kind of quality control we will use, or what kind of thinning we use to assimilate the rainfall. Okay. Yes. So now, similar to my earlier experiment, I also tried to assimilate rainfall also using the particle filter. So now I have a two framework. One is in which I can use rainfall assimilation using 4D bar, in which I use one tangent linear model. At the end of my time window, I assimilate the rainfall, come back using the adjoint model, adjust my basic parameters based on control variable, whatever I have in my model. Normally we use temperature, moisture, pressure, okay, winds. Then again did some correction, and iteratively we try to assimilate that. But in this particle filter point, we again use same thing. We assimilate the 6 hour rainfall, modify the weights, and every time step we do it like this. Okay, and this experiment I perform for a month long period, so that I also want to check up to what time period this procedure will valid. Because initially I think that maybe in my earlier experiment, because in that we only tried for 4 time steps. So I think that maybe it will not work after some time. So with this condition, I think that let us try this for a long period, and whether still I got some good result or my particle filter will collapse. Okay. So what we found that generally this is a one parameter ETS equitable. Yes, sir. Yes, yes, yes. Yes. Okay, okay. Yeah. So here. Yeah. X. Yes. 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 Okay. So now, because initially at x0 we don't have rainfall, but when we give a prediction for a 6-hour long, on here we consider 6 hours as a time window, at xt I have a rainfall value which is a accumulation of this period. So I use this as a model rainfall. Yes.
So if xt, if I call it xt as xp,
yes,
in
yes.
the background,
Yes, yes.
I want a analysis.
Yes.
And using the rainfall, observed rainfall, I need
Yeah.
to get. Sorry, I'm missing. What is the observation operator?
Yeah, observation of means okay. So observation operator means it will be defined at this time step where we have a okay, and here because in xt also we have a rainfall, and so now because both are in the rainfall domain, so
Only correcting the rainfall value.
yes, yes, yes. At the time, at that
Not any other state variable.
not any other state variable. So I selected particle based on the rainfall only at the end of my time window. So my operator will be simply say maybe a kind of a bilinear interpolation from model space to observation space. It's just like that.
And once you have the correct the analysis rainfall.
Yes, yes.
The analysis rainfall is not used in the model again.
No, yeah, here in particle filter it's not used, but in other space, yeah. But now we define one, we use the adjoint model. Now at this point, delta j by delta x0, now it will change my all other parameters here. Because my j is here based on rainfall, but this adjoint model will take care that how the change in rainfall will modify my other parameter, temperature, moisture, wind, etc. at the initial time step. I hope now it is clear.
It will not, because if you are using rainfall as part of the state vector,
Yes.
there is no, and it's just an identity operator.
Yes, sir.
State. It will not change the other variables, velocity, temperature, or whatever else.
But okay, but when in 4D bar like we are minimizing using the tangent linear adjoint model, at the end of window, at the end of my tangent linear model, I defined a cost function which is based on the difference of my rain from model and rain from observation. Now this difference, how it will change my analysis, initial condition, using the adjoint model. So now how much it will contribute, this difference of rainfall will how much contribute in the basic parameters. So like this, it will change the temperature, moisture and other fields. Okay, so now this is one parameter, ETS, equitable threat score. Yeah, so now here we found that not only for the low rainfall threshold, also for the high rainfall threshold, we got a improvement over the 4D bar methods. Okay, and again, because here again we are selecting the particles, rejecting the particles, again we give some perturbation based on scabs. So not only it changes or improving my rainfall prediction, it also changes my basic parameters, temperature, moisture, and winds. Okay, so like this, we tried this experiment and we found that this rainfall assimilation will be possible using the particle filter. Okay, so now this is a kind of an incomplete work. I did not complete it, but because I want to discuss this thing, it's a kind of a framework in which I want to use the deep learning method to generate large and large ensembles. So this work is somehow a extension of a analog particle filter developed by Langwens. Okay, he published this in MWR. So what he did, he generated catalogs. He used the Lorentz model. He developed the catalog, means at time xt, how it is related with the xt plus 1. So time xt is considered as a analogs, xt plus 1 is considered as a successor. Based on that, he demonstrated three theories: locally constant, locally increment, and locally linear. So he defined a model based on these theory in place of, and then he saw example of how this will work for the different filter ENKF and particle filter. Okay. So this problem is clear. So he considered a Lorentz model. XT states are considered as an analog. He made a data set of that. XT plus 1 data set is considered as a successor. Now he make a relation between XT and XT plus 1. Okay. And he defined this as an analog method. Okay. In place of using the actual computation, he used a kind of a fitting. So in this problem, we tried that in place of using a linear kind of a conditions, we use a deep learning model. It's based on the LSTM. Okay, and we use a relationship between analog and successor. So in place of solving the model, means in place of using MXT, I will use my machine learning based model. Okay, and then I can also generate machine learning based predictions. Okay, now my problem of solving the model at every time step is computationally less costly. And then we also tried the same framework with two different models, ensemble Kahneman filter and particle filter, for two different of catalog. One is small catalog of 10,000 members, another is a slightly large catalog. Okay, and then we just try to find out that whether in place of using the full model, if we will use the machine learning based model, whether we are able to use this way. Okay, the idea is that because now you know that there are many machine learning based model which are performing for some condition better than the ECMWF model. Like one is the GraphCast is there, then from China side Zoofi is there, then recently they developed AIFS. Okay, and in place of using a huge computational resources, within a very short time we can generate the model ensembles. Okay, so the one of the problem which we face is that how we can make our ensembles large and large. That can be maybe resolved using this type of framework. So we also tried something. We use two different methodology like CNN and GNN, graph neural network. We try to use the same data set, which is a long data set based on the era 5 reanalysis. Okay, and we also try to predict for next few days based on that. Okay, And then in place of using our model simulated forecast, we are using the machine learning based forecast, and then we are trying to use the this different filters. Okay, so initially we tried this for a Lorentz model, and now after getting some results, we think that we will do this for the full model set. Okay, so that's why this problem is not complete, but we found that in this case, for number of ensemble 100, the LSTM based model have a less error as compared to the whatever is developed by the analog data assimilation method. Okay, so that's why we named this as a deep data assimilation, because we use some deep learning based method here. Okay, so now there are huge number of techniques, and there are some issues, some benefits also. Okay, so it is totally based on your problem that which method is correct for you. Okay, so now here you can see that for non-Gaussian T there are some methods. For large system there are some methods. Some methods are not able to perform this. Okay, some method can be easily parallelized also, means if we have a huge number of computational resources, we can run multiple ensembles parallelly. Okay, so now I think this much only I have. So now there are different conditions you can work. There are mathematical problems, there are applications problem. Okay, so it's totally depends on you that which problem you want to do. Okay, and thank you. Now you can ask some questions. If possible, I will try. Okay.
Main motivation for particle filters is to address the problem of non-Gaussian.
Yes.
In the application that you showed, if you look at the distributions to see non-Gaussianity was
Yes, yeah, we start with,
specific variables.
yeah, like I start with the all sky radiances from the TIR channel. It's look like a binomial distribution. Rain distribution is a log normal distribution. So my assumption is that these parameters are not Gaussian.
Sorry, rainfall, you take rainfall at multiple locations at multiple times. That's a log normal distribution.
Yes, sir.
That's different from the distribution of the variable of interest.
Yes, yes.
So is it the observation operator which is non-low?
No, but in, yeah,
In the
but,
case of rain,
yeah,
one level,
yes,
rainfall, the observation operator is V.
yeah, operated, but
It's
the parameter itself is Gaussian. Yeah, it's a log normal. Its distribution is something like that. It's like, no. Or gamma distribution we also can use. Okay, so here my parameter itself is a not. Then in case of radiances, my radiated transfer model, my operator itself is a non-linear, non-Gaussian.
But did you actually, was it significantly, having non-linear operators does not necessarily give non-Gaussian distributions?
May. Yeah, may.
So was it actually?
Yeah, but when we plotted this thing, when we plotted the distribution of the all sky brightness temperature, is most of the time it's not Gaussian. Yes.
Last but one slide you showed about the number of ensembles.
Yes.
So, what is the improvement by increasing the number of ensembles?
Okay.
It is at some stage saturated.
In this work, TIR radiance assimilation. Actually, I was not able to do that because making huge number of ensembles from the weather model, it's took too much time in our place. So I tried only with this limited thing. But definitely, because if you go through this Miyoshi work, within that he showed something using the large ensemble, 10,000 ensemble he used. Within that he showed that how it will vary with the change of ensemble members. Yes.
What are the major problems to estimate
All sky radiance assimilation. Okay. So now presently for microwave, because for microwave, cloud is not a problem. Microwave can penetrate the clouds. Okay. So for microwave, ice and rain. These are the two conditions in which microwave data are not used. Okay. So now people start assimilating all sky microwave radiance assimilation in most of the places, in most of the operational center. Okay, so this problem is partially resolved. Clear?
that is due to the observation?
Yeah, that is due to the nature of microwave. Because microwave can penetrate cloud. For microwave, cloud is just like a clear. Okay, because you can penetrate this. So for microwave, there is a problem in ice and rain when microwave signals are scattered. So they develop the radiated transfer model for scattering, and after that this problem is resolved. Okay, now the next problem is coming for the IR radiances. Okay, IR, all sky radiances. Okay, so how we did, I will tell you. One problem is that when we start, because for simulating the all sky radiances, you need the hydrometers. Okay, like generally we consider our control variable as a pressure, temperature, moisture, winds. Okay, but suppose if you want to assimilate the all sky condition, in addition to this, you also need to consider hydrometer also as a control variable. Okay, so what we did, we make a one background error covariance in which Q cloud, Q rain, Q ice, snow, grapple, these are also my control variable. Okay, so this is the one thing which is required when you are going to assimilate the all sky. Okay, after that, okay, so this is one problem. So you need to make a background error covariance so that when you assimilate the all sky radiance corresponding to a small change in my cloud or rain, how much change will be distributed in other control variable. Okay, so this is one problem. Next problem is my radiated transfer model should be sufficient enough to simulate the all sky radiances, means simulate the cloudy conditions. So those models are available already. CRTM and also RTTOV, both model are able to simulate the all sky radiances. Okay, so this problem is also resolved. So after that you can use the next theory which told that my because what happened when we have a cloudy condition, suppose, so in cloudy conditions the observations are very highly correlated. Okay, so I can give one example, like suppose I have a different channels. Maybe someone told you that when we define one sensor, there are various channels in sounders. Few channels are peaking on the top of atmosphere, few are peaking middle of the atmosphere, few are peaking at the surface. Okay, so like this we have a multiple options. What happened when cloud is there? Okay, so in this condition, because in this condition, if I have a microwave sensor can penetrate this. So there is no issue. But suppose I have a one IR sensor. So what will happen? In case of cloudy conditions, my all channel will peak like this, because IR infrared is not able to penetrate the cloud. So what will happen? The another issue came is that my different channels are highly correlated. So this also we need to deal. Okay, so there are three problems. One is generating the background error covariance. Another is how to deal with this correlated observations. And then I think this two. Okay. So after that, you can assimilate all sky radiances.
Some centers are assimilating.
Yes, yeah, ECMWF is assimilating. I also assimilated this thing. Okay, so only thing is you need to develop this thing. Okay, yes. So because and there are some theories which they developed like ECMWF has developed this thing. They assimilated all sky radiances from infrared. Similarly, in Japan also, they assimilated the all sky IR radiances. Okay, so like this, but still it is not very popular in operational. Okay, means day to day people are not using all sky radiance assimilation, but in research mode, there are centers who are doing this. Okay. So we also did this work. We assimilated the inside water vapor channel, all sky radiance assimilation. We developed a framework in which we generate the background error covariance for all the control variables, include the hydrometer also as a control variable, and then we assimilate this.
Sir,
How?
actually you mentioned that we are using only around 5 to 7% of all the observations for the assimilation.
Yes.
So, however, suppose if we are able to manage other observations to include in our experiment, and we are limited by the computational resources. So, how to overcome this problem? Basically, computing cost. Are there any mathematical approaches to handle the observations?
No, actually, the problem is that how we select the observation. Like satellite will give you observation in different frequency, like visible. Visible radiance is also available. But now only people are able to assimilate, means after almost 60 years, now people are able to assimilate visible radiances. Okay, so still there is a gap. We don't know the operator also. Like there are few parameters which are available from satellite, and we don't know how to make an observation operator. So that's maybe in this regard to develop the operator, maybe machine learning will be helpful, because now people are generating observation operator also using the machine learning. Okay, so the problem is not that we are not problem is that we are not know few things, like we don't earlier we don't know how to simulate the visible radiances, okay, using the some fast model RT model.
Yes.
And if you take the proportion, the visible is available at the finest resolution, 1 kilometer here in inside case. Okay.
Mm.
So it's not a problem that we are facing the computational problem only. We are also facing the problem, theory problem, how to make the observation operator, how to use that data efficiently, how we can avoid the thinning. Okay, so these are also issues.
Yes. Okay, thank you so much.
If there are no more questions, let us thank Dr. Prashant Kumar for an excellent lecture.
Thank you, sir.
We now break for tea.